In question number 7, there is an infinitely long straight wire carrying charge with linear charge density lambda is equal to 2 microcoulomb per meter. Calculate the potential difference between 2 points A and B which are at distances 5 meter and 10 meter respectively from the wire in kilovolt to the nearest integer. So let this is an infinite wire, this is point A and this is point B. The wire is charged with linear charge density lambda. Its distances from here are RA, that is 5 meter, and RB, that is 10 meter. So it is a standard case. We know that the potential difference VA minus VB is given by lambda divided by 2 pi epsilon naught ln RB by RA. Because in the direction of the electric lines of force, potential decreases, so the potential of point A is more than the potential of point B. So if I substitute the data, the value of lambda is 2 into 10 raised to the power minus 6. So if I multiply and divide by 2, then it can be written as 2 into the value of 1 upon 4 pi epsilon naught can be written as 9 into 10 to the power 9 into ln 10 by 5. So that is ln 2. So the value of ln 2 is 0.69. So if I substitute this, it comes out to be 25 into 10 raised to the power 3 volt or 25 kilovolt to the nearest integer. So the correct answer for question number 7 is 25. Let's move to question number 8. In question number 8, the electric potential inside a charged sphere is given as V is equal to minus 4AR square plus 3B, where R is the distance from the center of the sphere and A and B are constants. Then the volume charge distribution inside a sphere is given by rho is equal to NA epsilon naught. Find the value of N. So we know that rho is constant because the value of N is an integer and A and epsilon naught are constant. So we know that the E is given by electric field is equal to minus dV by dr. So that is equal to minus of, so if I differentiate the electric potential function with respect to R, so that can be written as minus 8AR. So the value of electric field is equal to 8A into R. Now I am considering a spherical shell of radius small r. So the radius of this spherical shell is small r, and I am considering another shell of radius r plus dr. So there is another shell over it and this thickness is dr. Now if I consider the charge enclosed in this region, the charge enclosed in this region is dq, that is enclosed, and if I consider the flux due to this enclosed region charge, then I can write phi can be written as E into A, or d phi can be written as E into dA plus A into d. So due to the given charge distribution, we can write the value of dE as, this is 8A into dr. So d rho, so from the Gauss law we know that integration of E dot dA over a closed loop is equal to Q enclosed divided by epsilon naught. So this can be written as Q enclosed divided by epsilon naught. So volume charge density rho into volume is 4 pi r square into dr of this segment divided by epsilon naught, and that is equal to E. So the value of E is 8AR into dA. So the surface area of this spherical shell at a distance r can be written as 4 pi r square, and if I calculate dA, that can be written as 8 pi r into dr. So the value of dA is 8 pi r into dr plus A, that is 4 pi r square, into d. So the value of d is 8A into dr. So if I solve this equation, the value of rho comes out to be 24A epsilon naught. So on comparison, the value of n comes out to be 24. So the correct answer for question number 8 is 24. Let's move to question number 9. In question number 9, two free positive charges 4q and q are at a distance L apart. Find the magnitude of charge in microcoulomb needed to achieve the state of equilibrium of the entire system of 3 charges. And the value of q is given as 81 microcoulomb. So two free charges are given. Let this is 4q and this is q. Now, in order to have the entire system of 3 charges to be in equilibrium, a negative charge must be kept in between the 2 point charges. Let the negative charge q dash is kept at this point. So let the distance from the charge q is x, then this separation would be L minus x. So if I see the force on charge small q, then the force on charge small q due to 4q is in this direction, and due to charge q dash, which is negative, is in this direction. So if I write the equation, then I can write 1 divided by 4 pi epsilon naught q into 4q divided by L square, that must be equal to 1 divided by 4 pi epsilon naught q into q dash divided by x square. So this is my first equation. Similarly, if I see the force on charge q dash, then due to 4q, the force on q dash will be in this direction, and due to q, the force would be in this direction. So due to q, it can be written as 1 upon 4 pi epsilon naught q dash into q divided by x square, and due to 4q, it can be written as 1 divided by 4 pi epsilon naught 4q into q dash divided by L minus x whole square. So we can equate these two. So this is my equation 2. On solving equation 1 and 2, we will get the value of x is equal to L by 3 and the value of q dash is equal to 4 by 9 of q. So if I substitute the value of q, that is 81 microcoulomb, so the value of q dash comes out to be 36 microcoulomb. So the correct answer for question number 9 is 36. Let's move to question number 10. In question number 10, a metallic sphere of radius r is given charge q. The electrostatic force exerted by one half of the sphere on the other half is given by this expression. So we have to find the value of n. So this is a metallic sphere of radius r. The charge q is uniformly distributed over this metallic sphere. So we can find out the surface charge density sigma, that is q divided by 4 pi r square. The radius is r. Now we have to find out what is the electrostatic force experienced by the one half of the sphere due to the other half. So we know that the electrostatic pressure acting on the sphere is given by sigma square divided by 2 epsilon naught. This electrostatic pressure is same at the every point. So in order to calculate the force exerted on one half, can be written as electrostatic pressure, that is sigma square divided by 2 epsilon naught into projected area. So the projected area of the half segment is pi r square. So if I substitute the value of sigma in this equation, then we will get q square divided by 32 pi epsilon naught r square. So on comparison, the value of n comes out to be 32. So the correct answer for question number 10 is 32. Let's move to question number 11. In question number 11, two identical parallel plate capacitors, each charged with 10 microcoulomb, are connected in parallel. At t equal to 0, the distance between the plates of first capacitor begins to increase uniformly as d1 is equal to d0 plus vt, and the distance between the plates of the second capacitor begins to decrease uniformly as d2 is equal to d0 minus vt, where the value of d0 and v is given. Find the current in the connecting wire at t equal to 0 in milliampere. So we have two capacitors. One is this. The charge on this capacitor is 10 microcoulomb, and that at any time t, the separation between them is d0 plus Vt. So the capacitance C1 can be written as epsilon 0A divided by d0 plus Vt. Similarly, the second capacitor separation is decreasing, its separation is increasing, and at any time t, the separation would be d0 minus Vt. So the capacitance C2 can be written as epsilon naught A divided by d0 minus Vt. So if these two capacitors are connected in parallel, then the potential difference across the capacitor will remain same. So the charge Q1 at any time t on the capacitor 1 can be written as Q1 is equal to C1 divided by C1 plus C2 of total charge. So total charge on the isolated system of these two capacitors is 20 microcoulomb. So that is Q total. So the value of Q total is 20 microcoulomb. So if I solve this, then this comes out to be d0 minus Vt divided by 2d0 into Q total. Since the capacitance of capacitor 1 are decreasing, so the charge on the capacitor 1 also decrease. So the current through the connecting wires I can be written as minus dq1 by dt. So it comes out to be V divided by 2d0 into Q total. So if I substitute the data, the value of V is 10, the value of Q total is 20 microcoulomb. So 20 into 10 to the power minus 6 divided by 2 into d0. So the value of d0 is 10 to the power minus 2. So on further solving, it comes out to be 10 raised to the power minus 2 ampere or 10 milliampere. So the correct answer for question number 11 is 10. Let's move to question number 12. In question number 12, two capacitors C1 and C2 are connected in series as shown in figure. Their breakdown voltages are 12 kV and 8 kV respectively. Find maximum safe voltage in kV which can be applied across points A and B. Since the given capacitors are in series, so the charge on them will remain same. So if the potential difference across AB is VAB and the potential difference across C1 is V1, then we can write V1 is equal to C2 divided by C1 plus C2 of VAB, and this value must be less than or equal to 12 kV. So if I solve this, the value of VAB from here comes out to be 12 kV into C1 plus C2 is 3 divided by C2. So from here the value of VAB comes out to be less than or equal to 18 kV. Now the same procedure I have to apply on this C2. Let the potential difference across its V2. Then V2 can be written as C1 divided by C1 plus C2 of VAB, and this V2 must be less than or equal to 8 kV. So again solving, the value of VAB less than or equal to 8 kV into 3 divided by 1. So the value of VAB is less than or equal to 24 kV. So from these two equations, this and this, we can say that the maximum safe voltage which can be applied across point A and B would be 18 kV. So the correct answer for question number 12 is 18. Let's move to question number 13. In the question number 13, in the arrangement shown in figure, find the potential difference in volts across A and B. So let the potential of this point is 0 and the potential of this point is X. Then we have to find the value of x. If this potential is 0, then the potential of this point to be 30 volt and the potential of this point to be minus 10 volt. So again applying the nodal analysis, that is the charge on the isolated system will remain constant. So we can write in this way: 2 into x minus of minus 10, that is x plus 10, plus 3 into x minus 0 plus 5 into x minus 30 must be equal to 0. So on solving this equation, the value of x comes out to be 13, and it is the potential of this node, that is 13 volt. So the potential difference VA minus VB is 13 volt. So the correct answer for question number 13 is 13. Let's move to question number 14. In question number 14, a ring of radius 20 cm is uniformly charged with under root 12 microcoulomb of charge. A particle of mass this and charge this is released from rest on the axis of the ring at large distance from the ring. If the ring is fixed, then find the maximum acceleration in meter per second square attained by the particle. So let's analyze the situation. Suppose this is a ring of radius r. The value of r is given in the question, that is 20 centimeter. So 20 into 10 raised to the power minus 2 meter. The charge which is uniformly distributed over the ring is under root 12 microcoulomb. So that is Q. Now, if I consider a particle on the axis of this ring which is at a far distance, let here mass is m and charge is q, the value of m is given as 10 gram. So 10 into 10 raised to the power minus 3 kilogram, and the value of q is minus 1 into 10 raised to the power minus 6 coulomb. So in the question it is asked when the charged particle would have maximum acceleration. So we know that in the region of the electric field of this ring, when the electric field is maximum, then at that point the charged particle would experience maximum electrostatic force and it would have maximum acceleration. So we know that if we draw the electric field distribution graph with respect to r, then this is the variation of the electric field with respect to r, and at this point the electric field is maximum, that is when the value of x is equal to r by root 2. So the force experienced by this charged particle at this point would be q into E max. So that can be written as 1 divided by 4 pi epsilon naught q into x, that is r by root 2, divided by r square plus x square, that is r square by 2 raised to the power 3 by 2, and this is equal to mass, that is m, into acceleration. So this would be maximum. So if I substitute the data and solve for A max, then the value of A max comes out to be 30 meter per second square. So the correct answer for question number 14 is 30. Let's move to question number 15.